No, good morning and good afternoon to everyone, and welcome to the meeting. The first talk of today's session is given by Klaus Kroy, and the title of the talk is Microswimmers, Activity Landscapes and Retarded Interaction. So please, Klaus, you can start.
Yeah, thank you very much for the nice introduction and for the invitation. Of course, I'm very happy to be here in this beautiful workshop, and I really enjoyed it so far, and the opportunity to ask questions and to really understand something, learn something. In my group, I work on active particles, and we also work on flows, but normally the two things are not closely linked together. And so I will show you a bit, give you a bit of an overview. And in particular, I will also the topic of the talk itself is a bit, as you see, it's like an overview with different aspects. The microswimmers themselves, how do they work, and in real life. Then what do they do in activity landscapes? How do they behave there? And what is the effect of retarded interactions or delay effects in the motion of the microswimmers? And very much of this is a very close collaboration with Frank Zicher's group in Leipzig. That's the experimental group, and I show some of their experiments and also some of their results, some new results also that most of you probably haven't seen yet. And so I hope that you enjoy also this experimental side of the story. Apart from Frank, a lot of input came from Viktor Olobach. He was a Humboldt postdoc with me for a couple of years, and he's now in Prague building up his own group. And he's kind of the workhorse of the whole talk, I would say. And there is then also contributions by some other people who worked with me in the past, like Gian Maria Velasco, who is in the meantime no longer in Luxembourg, but started his own group in Italy. And a former postdoc from India, which I also mention here. This is Dipanjan Chakraborty. And then a few PhD students, former and present in the group. So let me start by showing you something that's not a topic of today's talk, but that's what we do, where we use some concepts that you're very familiar with, turbulent flows and problems of particles in flows. And that is what you see here. So I won't go into that except for this one page here to show you what it is. So we are really looking at structure formation in the desert by wind-blown sand. And you see a picture on the left from our work and also on the right to recent papers. And there, the problem is that the wind picks up sand grains and they hop over the ground. And from that, a lot of interesting structures emerge, not only on Earth, but also on extraterrestrial bodies, like on Mars or even on a comet. They have found such sand waves. And it's quite amazing how many different type of structures that all look a bit similar but are not identical you can get from this problem. And so this is really a field where a lot of things have been, of course, discussed in the literature all over and are still discussed all over the whole time, especially also regarding structures on Mars and so on. But there is still no really deep and complete understanding, and that is partly related to the complexity of the turbulent flow of the wind. And so, yeah, I think that could be interesting for some of you with a strong background in turbulence to see to have a look on this field and see what are the problems there, and what's not understood, and what's still under debate at that point. Yeah. So I just mentioned one thing that to give you a feeling. And that's if you look on the plot on the right here, you see in the front, you see some little ripples as you see them on beaches very often. And in the background, you see a large dune. And in between, you see some larger thing, which is a bit intermediate between a dune and a ripple. And that's called a mega ripple. And the interesting thing, why it is there, we believe, is that the sand is sorted by the wind, so into light grains and heavy grains, or fine grains and coarse grains. And you see in the bottom left of this picture an inset here where we show grain size distributions, and you see that they are more or less bimodal. So there are two fractions of sand that have sorted themselves over time due to the action of the wind. And that's what explains then why a certain structure can emerge there. And yeah, quite often people have measured this for many years, for decades, and you find a huge complexity, and it looks very confusing often. And just to mention, like you see the plot on the right where it looks like you get a cloud of data, and there is no clear idea whether there is any regularity really in these data, and they just look like a wild cloud. And that's what happens quite often. But yeah, if you dig into it, and that's so I give you this one example of an interesting discovery which we made recently. You can show that in these bimodal sand size or grain size distributions, there is a hidden invariant. And this is, if you plot it on a log scale, the grain size distribution as done here, the width of the coarse grain peak, so the right peak here, peak on the right side, the width of that is essentially constant over a huge range of environmental conditions and grain types and grain sizes, and including ice particles and particles on Mars and whatever. And so on Mars it's a bit different from Earth, but again quite uniform as far as we have seen. There's not so much knowledge about the grain size distributions on Mars, obviously, compared to Earth. So yeah, that is interesting. You see a really messy and complex system, but there is some regularity hidden underneath. And so yeah, that is related a lot also to the turbulent transport. And as I said, not everything there is understood. By far, not everything is understood. So I will leave it with this just as a teaser for you, if some of you have the background to yeah, maybe look into that and then get interested in that. There is another thing that distracted me a lot from the stuff I really want to tell you today, and this is this here. Yeah, I have been much concerned about what's going on politically recently, and pretty worried today in particular because there is a debate in the German parliament where people decide about our future who understand very little of what I summarized in this little review there. So if you are among those who are a bit concerned about what's going on, you can have a look maybe at this archive paper. Okay, so I now switch to the real topic, namely the active particles. And I show you the real active particles that Franciscus is building and using in his lab. And yeah, for many purposes, they use these Janus particles but they have also other particles. But yeah, let me just show you a bit the Janus particles. They are the most commonly known particles. And an important aspect here, as you see, is that they break a spatial symmetry. And then you also break another symmetry, namely you add energy on the scale of the individual particle. So these big atoms, or model atoms, so to speak, if you have many of them, they can give rise to nice collective phenomena, but you have broken some symmetry on the microscale, on the scale of the particle. Yeah. And on a coarse-grained level, you've seen this in the previous talks already. We can describe those particles with a rather simple diffusion model, where we have white noise driving the particles, shaking them, and rotationally and also translationally. And there is a particular term then here that might be an external force, let's say, but here is a particular term that gives them some velocity. So they are moving if you give them a given amount of fuel that is constant, and they move with a constant speed. The direction is fluctuating, yeah, and so I show you a little movie here that you can see how this looks like in the lab. You see such a particle that's now just diffusing ordinary Brownian motion, and at some point they switch on the fuel, and in this case the fuel is just light that heats the particle, and it, because of the particle is half coated with gold, as you saw in the microscopic image, it then gets asymmetrically heated, and it starts to swim, as you can see. So now you get a much faster, still more or less diffusive, but persistent diffusive motion. And one particular aspect that they are using a lot in Frank Zicho's lab, you see on the right. So on the right, you see that these particles can be steered. And steered means not that you push them around by forces, but you tell them where to go by looking at the direction into which they are pointing at a moment. And if it's the right direction for your purpose, you give them fuel. And if they decorrelate from the direction that you like, then you switch off the fuel. So they become a bit like run and tumble, if you wish. But you start the runs always in moments when you think it's good for them to go where you want them to go. So this is like pushing them around where you want them to be, but not touching them, not pushing them by force, but just giving them fuel at the right moment. Yeah, Massimo, you have a question.
Yeah, just a curiosity. The moment you switch off the light, how many seconds? I mean, what is the time scale to be back to be a Brownian particle?
Stopping time is, for our purposes, it's zero, right? These particles are relatively big, and they are in water, in aqueous solution, and so the stopping times, well, relatively small. What's to say? They are kind of big colloids, but still, big colloids, they are just for convenience, but still relatively small. They are much smaller than the sand grains in the turbulent flows that I was mentioning before. They are like below micron scales.
Thanks a lot.
And so the stopping time here is practically zero for all purposes. Yeah. So that is a technique they have utilized a lot, and we can do certain things with that. And that's interesting in the context of swimmers, to have such a method to make the particles do what you want without pushing them by force. Because one of the difficult questions about swimmers is really that a true swimmer does not take force from the outside. So a true swimmer is like a motorboat that has its own engine, propel it, and it's not a sailboat that is driven from a wind or a force that comes from the outside. And so this difference is subtle because the flow fields change if you start to add forces to the particle, and so people have there has been a lot of confusion in the past about this aspect, also in terms of the models that people use, where they quite often replace the true swimming pattern or the true swimming motion of the particle by a forced motion, and then you have to be very careful to not come to wrong conclusions. Okay, so you'll see. I'll come back to that later when I describe some experiments. So one aspect of this fueling the particle by heating it is that, yeah, the particle itself, even if it's not an asymmetric Janus particle, if you forget about it for a moment and assume it's a homogeneous particle, a homogeneous sphere, its fluctuations will not be equilibrium fluctuations, but because of the particle being hotter than the surrounding, there is a constant temperature. There's a temperature gradient, constant heat flux from the particle to the bath, so the system is not in equilibrium. And of course, that means, okay, we are breaking a symmetry here. Energy is not conserved, but also there is no unique temperature anymore in the problem. And also that breaks a symmetry. And so we can't simply say, oh yeah, we know there's the Boltzmann factor and so on, because you don't even know what is the right temperature to put into the Boltzmann factor. And but this problem can be cured, as we have shown in the past, because you can really very well from first principles, you can, or like hydrodynamic techniques ultimately, because it's a Brownian problem where we have a scale separation, you can really quantitatively describe these non-equilibrium aspects of the hot fluctuations. And that is because the Gaussianity of the fluctuations is broken, but it's very weakly broken. So if you treat the problem as a completely linear problem and the fluctuations stay Gaussian, you make a conceptual mistake to some degree, but it's irrelevant for in practice. And so we can calculate practically everything about the motion of the non-isothermal fluctuations of these particles. And this also works if they are Janus particles. And then they are moving, as we saw, but superimposed on this motion are these hot Brownian fluctuations. And we can describe them in very much detail. And here on the left, you see different measurements that we've been done that show an effective temperature. Like if you see my movie and if you evaluate the mean square displacement and then you extract the Brownian temperature, if you don't know what it is, yeah, you just say, oh, this is Brownian motion, you extract the temperature there, then you'll get an effective temperature, and this we can calculate. That's basically the take-home message here. And we can calculate it for several or different degrees of freedom, and the effective temperature that you get is different depending on which degree of freedom you're looking at. So if you look at rotation, the particle looks like in a hotter environment. If you look to translation, it looks like a cooler environment. And so, yeah, but you see from this comparison of numerical data and theory that we do understand this very well, even for this Janus type particle there. So in a sense, we can encapsulate this part of the non-equilibrium problem here, which is really a subtle one in the end, but for practical purposes, it's encapsulated in a bunch of effective temperatures in the end. On top of these fluctuations, then there are flow effects, of course, as like even if the particle is isotropic, if it's heated, like you have the temperature gradient in its surrounding, that will of course excite thermophoretic flows in the surrounding. So if we go to more than one particle, if we have interactions between particles, as was often mentioned in previous talks, then there are hydrodynamic interactions between these particles, of course. But on top, there are interactions here that come from the engine, from the fuel that you give to the particle, which gives this temperature profile and excites phoretic motion in other particles that are nearby. And here you see a very simple setup where we were able to quantify this in complete detail experimentally with Frank's group, and by parameterizing the data or fitting the data with a model. And it turns out that this is pretty complex, and in particular, the apparent interactions between two particles are non-reciprocal. And you have to keep this in mind. If you say, oh, let's make a model of swimmers and so on, and they interact, maybe they attract or they repel. So you have to keep in mind these interactions are not like potential interactions; they are non-reciprocal. And you see here just in this on the right, you see some data, of course, and you see how it's done. So you have a little gold particle that's heated by the laser. So in the surrounding of the gold particle, you get such a temperature gradient in the flow, and then you put a just non-heated, it's not touched by the laser. You put some Janus particle there, and then you see how it behaves in the gradient. And so if you do such an experiment, of course, it's useful that we have this technique of bringing the particle back by the nudging technique to tell it to swim back if it's gone away, if it's gone out of focus. They bring it back with a swimming trick. Let it swim back, not push back. And in this way, we know that this is a force-free system, and that will come up again in other aspects, that we are not putting forces on these particles. Okay, so here on the right, you see then some little arrows that show you what the local surface flow slip velocities on the surface of the particle, what they are. These are the velocities that drive the swimming motion, and they depend on the relative angle of the particle axis, the swimming axis, to the heat source in a complex way, as you see in the last picture here. This scheme here in schematic in D shows you that the resulting velocity is not along the axis of the particle, but has a complex dependence on the properties of the particle, like its thermophoretic mobilities of the two hemispheres and the angle with the heating source. And so you can imagine, if you have several such particles, some of them hot, some of them maybe not, or all of them heated, but the interactions are relatively complex. But they are, for this particular system with the heating, they are now really very precisely known. So if you ever should want to know what they really are for such a swimmer system where they can be measured, and here they can be measured, it's a nice system where you can really measure these interactions in detail and really nail it down to the thermodynamic mobilities and phoretic mobilities and so on, that you need to describe this on the particle level. So in this paper, it has all been worked out. Okay, so that's how these particles work. And now, okay, I've already mentioned that there is some symmetry breaking going on, and some of that is maybe not so important, and some of that is, and so that has, I think, motivated this question here formulated by these people in this physical review letters some years ago. I said, okay, how do we quantify how far a system is from equilibrium if we are dealing with active matter, where all the individual particles are really off equilibrium already? So is there a good metric to quantify how much we are out of equilibrium, or how much we can go back and use our equilibrium concepts? And then what they write here is that, of course, somehow the gold standard to measure how far you are from equilibrium is that you look at the entropy production. And if there's a lot of entropy production, you are further from equilibrium. If there's less entropy production, you're closer to equilibrium. And that's a objective metric, and it would be really good to know this quantity. Then you know basically how much time reversal symmetry is broken, and this relation between breaking of time reversal symmetry and entropy production rate is the essence of some of these fluctuation theorems that people discuss in stochastic thermodynamics. But they also write, it's hard to compute and even harder to measure experimentally, and has been little studied. But in fact, we did this with Frank also, and you can do this very nicely for such a microswimmer as like one of his microswimmers. You heat it and you look at it, how it goes, and you just analyze the trajectory, and you can do this for a very long time in the lab. And so we did this both for a simple model of this microswimmer and theoretically, and also we did it in numerical simulations using all atom representation, so to speak, with Lennard-Jones atoms, and of the surrounding liquid and the particle itself, and experimentally in the lab. And then we put all this together and looked what comes out there. And we are looking at this fluctuation theorem here, or we were at the time, and how much more likely is the particle to go forward if it's a swimmer. The fluctuations are not isotropic anymore, but they are biased in the forward direction. So how much more likely is it to go forward compared to backward? And we did this also for the angles, by the way. So you can also ask how much is it more likely to go in at a certain angle, at a certain direction, and so on. And I show you only the forward-backward symmetry breaking here, and you see, okay, if you take the logarithm of this fluctuation theorem, then you see that the logarithm of this ratio of probabilities to go forward, go backward, or produce entropy or destroy entropy is linear in the motion of the particle. So here there is the J is the flux of the particle, like its motion in the direction along its axis. And you see it's a beautiful straight line, which shows that there is such a fluctuation theorem. It holds very well. And the parameters that go into this are now these encapsulated non-equilibrium parameters that I was speaking about before. So the whole question here of how much I break the equilibrium and so on is already on the level where I'm using these effective temperatures and effective parameters that we discussed before. So the equilibrium is already broken, but now it's broken on top. So we have a stacked up hierarchy of non-equilibrium effects. And if we can get the first ones well under control, we can use them to address then the higher level ones, so to speak here. And those are then the dominant ones for the question of how far you are really from equilibrium, because the other ones, I subsumed them into renormalized equilibrium parameters, so to speak. So this is a mild form of non-equilibrium in a sense, even though it's far from equilibrium technically, but it's mild in the sense that I encapsulated these problems into effective parameters. Yeah, and then I can discuss the breaking of equilibrium here using these uncertainty relations, which were we were with this paper, I guess some of maybe among the first people to check such a relation, and also the fluctuation theorem, and can use those metrics then to quantify what's non-equilibrium here and what not. Okay, so yeah, that's a bit the conceptual background for us, how we work with these microswimmers and how we think about them and what we are interested in there. And now I want to show you two toy problems that we addressed using these microswimmers. So yeah, you've seen that we understand them reasonably well, but now we want to do some practical applications. And yeah, the first one is purely theoretical. There we do not have own data, but we looked at data from other people, other groups. And the second one is again together with Frank Zichos, where I show you the data from his lab. And well, the first one maybe is a bit not so urgent to most of you. It's about an active heat engine where you have a particle in an optical trap, say, and you look at its Brownian motion, but then you can modulate the trap, so you can basically compress its Brownian motion or relax it, and then you can build a heat engine. And then the basic idea is, okay, let's do this not just in a solvent like water, but let's put into the surrounding some active particles, or, which is kind of very closely related, make the working medium, which is the blue particle here in the right plot. Yeah, we can make this a Janus particle again. This is something very similar to making putting an isotropic particle, but in a bath of active particles. And people have realized this setup using bacterial baths, for instance. So the red particles would be bacteria that swarm around, and you put the probe inside, and then you can build a heat engine with this probe particle, where the probe particle is the medium, the working medium. Now, even though maybe you're not that much interested in the heat engine, and I want to speak about it briefly because it is, giving you some. People have claimed that they can break the second law, which they cannot. Yeah, and in the second problem, I will show you that there are nice patterns coming up if you have regions where there is activity, and then there is a region where there is no activity. And then at the boundary between these two regions, there is interesting patterns coming up. And I realized that I'm already running out of time. So I have to probably have to stop already very soon, right? Who's the chairman again? Should I?
No, you have time. I mean,
I have a bit more time.
Yeah.
How much?
I say 10 minutes for the talk and 15 minutes if you want for Q&A, or
okay.
something more for
10
the
minutes.
talk.
10 minutes is okay. Okay, good. Okay, so good. So let me first speak about this heat engine briefly. And there are two types of heat engines really that people have discussed a lot with active baths, where the heat bath is a suspension of active particles, of, for instance, bacteria or other active particles. And the steady state engines, they turn steadily, like you see the skier here. It wouldn't turn in an equilibrium setting, but if there is a bacterial bath in the background, it will start turning, and thereby signal to you that it's in a non-equilibrium bath, because otherwise this would be forbidden. And on the right-hand side, you see something that's more in the spirit of what we've described in the paper, is a cyclic heat engine. And you have to distinguish the two, and they have you need different approaches to them and to quantify their efficiencies and so on and so on. But the funny thing is, for both engines, which in the end ultimately do just, I mean, there is the heat engine here, and it's related to some work reservoir. It does some work. Typically, it exports some work to the outside. And it is related, it is then linked to a heat reservoir. That's a classical equilibrium heat reservoir. Typically, it's the solvent, it's a background solvent. But then there is also this non-equilibrium aspect of the reservoir, which would be the bacteria or whatever active particles you have in the solvent on top of that. And so the idea is basically that if you forget about all the food that you have to give to the bacteria and so on, you call this some effort you have to do, but you don't count it, then you want to really know how discounting the so-called housekeeping heat, just looking at the active heat. So how much is the collisions with the particle really driving my working medium, which is the colloidal particle here, and how much is this giving me maybe a good efficiency for my work production. That's what people really look at. And then they come up in both cases with claims that they have violated the second law, which cannot be and is not the case. But where do these claims come from, right? Or why did people make these claims? And it's kind of a bit subtle aspect. So if you want to speak about these heat engines and the efficiencies in the context of the second law, you need to understand temperature. And temperature is normally taken for granted in thermodynamics because you have a zeroth law of thermodynamics, which tells you that there is equilibrium. If there is something hot here, it will heat the rest, and then there will be some equilibrium. And it's the zeroth law that can be broken, of course. If we go out of equilibrium, then we do not have an isothermal situation. So we break the zeroth law, and that affects how we speak about the second law, because there is a temperature in the second law, so to speak, and this temperature does not necessarily have to be unique. So there is a temperature in the sense of the second law, and we have to find this and define it properly, and then we can understand why the second law is not violated in such applications. And so in this model that we discuss here, which is an active Brownian particle in this harmonic trap, we can very nicely demonstrate how this effective temperature comes about, and we can calculate it exactly. So it's again a bit a similar story as before. We can calculate this effective temperature and thereby map back this problem, non-equilibrium problem with an active heat bath, to problems that we know how to deal with. And you see on the right that there is a solvent temperature protocol. Solvent temperature is raised and then it's lowered again, and the trap stiffness K is going up and down and kept constant and so on. That's the cycle, it's a Stirling cycle. But then the effective temperature that really matters in terms of the second law, the temperature that you need to formulate the efficiency, Carnot efficiency or Stirling efficiency and so on, that you see on the right is a pretty complex function of time, and that's not something you control from the outside. That's something you have to calculate. And I just show you for illustration, without going into the details, I show you how this is calculated. And you see it's a set of coupled equations, and they are the relevant quantity, or the central quantity there is the mean square displacement, or the variance of the position of the particle, which is the sigma. And that's the essential degree of freedom that is really dealt with here in this heat engine. It's really confining and relaxing these thermal fluctuations. And that's the central quantity that you have to relate to a temperature. So Massimo, you have a question? Yeah, please.
So if I understand correctly, the first formula, the first equality, essentially you are exploiting Einstein relation between temperature and diffusion coefficient, right?
Yes.
So this is not, I mean, it's strange because, I mean, you are out of equilibrium, but you are using something which is defined at equilibrium, no? Or
Yes, yeah, exactly. I'm saying here that what we calculate is really the diffusivity, right? And as you say, we use the diffusivity to really define an effective temperature that we plot there. And in this step, as you say, I'm basically like the technical quantity to calculate here is the dF, of course, right? Like the effective diffusion coefficient.
Sure.
And then I do this mapping back to a description that deals with the active solvent as if it were a thermal heat bath. So at this step, which is, as you rightly point out, is not, you know, a given equality, but it's kind of a definition here.
Okay, so it's a sort of the equivalent heat bath if you would have been at equilibrium. Okay,
exactly. So that's the same as with the hot Brownian fluctuations. Again, I'm searching for a notion of temperature that replaces my classical notion of temperature, but it's a non-equilibrium temperature, and it's calculated here. And then I have to see whether this mapping is allowed and works, or if it doesn't.
But I mean, what confuses me is the following: that if you would have used the other no relation between the temperature and other, I don't know, coefficient, transport coefficient, or other properties, in principle, you could have obtained a different temperature.
Exactly. So, as I showed before, also for the hot Brownian particle, you get a bunch of temperatures, and then you have to really decide which one is the degree of freedom which is doing the work. What's its temperature?
Okay.
What's its temperature, equivalent temperature? Yeah, that I have to decide. And if I get this wrong, I of course violate the second law, right?
Of course.
And in the sense of you know, writing down an efficiency, a Carnot efficiency with T hot, you know, T cold, T hot, and ratio of T cold, T hot, and so on. I violate it if I grab the wrong temperature, and so you need basically to you need a thermometer that really measures the degree of freedom that is relevant for the engine and for its efficiency. And there are limitations to this, because like in the end, if you go on and look at this, then the fluctuations become non-Gaussian, and then it becomes increasingly questionable whether you can reasonably assign such a temperature. But in this case here, it's really, you can show that all the thermodynamics you really want to do only depends on the variance of the particle, because it's such a simple setup. It's 1 degree of freedom, and it's a linear. We do it. It's a linear problem. Yeah, we have basically a harmonic trap and so on. If you go to nonlinear, you run into exactly the problem you point out. You get many different notions of temperature. You don't know how to apply them in general, and you would have to work very hard to make any progress. You get an infinite hierarchy of notions of temperature that would matter in this case. But here it's a linear problem, and there you can do it precisely, basically.
Okay, thank you.
And so there is a basic knowledge how to start this. Yeah. Okay, thanks. So I'm really running out of time, but okay, it's a pity. So let me switch to the next problem, and give me 5 more minutes here. So here we have now the microswimmer. Let's say the same microswimmer, but it's in a little device there and where there is one part is, if it's in the green region, the laser is switched on, then it's an active particle. If it's crossing to the blue region, the laser is instantly switched off. So it's instantly a passive particle, only doing normal Brownian motion. And now, if you have this, how does the distribution of the particle look like? What's the density distribution, and what's the orientational distribution of the particle? And it turns out that this looks interesting, as you see on the right. So on the top, you see the top view, passive active region. Below, you see the density profile. So the particle is much more often in the passive region where it's just doing nothing most of it. So these measurements go for days, yeah, and then it's here on the right hand side where it's active. It quickly leaves again out of the active region, and to keep the particle for a day in this box and measure it, there is again the nudging technique is employed to make it swim back and to then go further with the measurement. So again, we are not putting any boundary forces or so, except from the top and bottom plates there. And so you see, you get this interesting step-like density profile. So you also see the theory there, and then below in the lowest panel, you see that there is orientation of the particles associated with the density profile, and you can easily understand it. You know, if you're in the active region and you're driving towards the passive region, and if you enter the passive region, you get stopped. So you have typically, if you enter from the active region, you're looking inside the passive region. If you're going from the passive region to the active region and you are looking, that direction is into the active region, you will quickly drive away from the boundary and you will go somewhere else and you will be gone from the boundary. Only if you're looking backwards at your passive region and then you cross by accident, then of course you're pushed back immediately and then you stay near the boundary. And so from this simple consideration, you can already understand why there is polarization and why polarization is linked to the density step there. And it's interesting that, you know, much of this can be calculated basically exactly, but it's not quite true. But it wasn't understood, or much of that wasn't understood until recently. So when we published the paper, there were other papers before who got it wrong, and there's it's a bit of a tricky thing how you technically approximate the equations to calculate this. And here I show you some of the results, but I don't enter into details. Just to tell you, this density ratio that's written there upside down here it goes like the square root of these diffusion coefficients in the effective diffusion coefficients in the passive and in the active region. And the square root wasn't known, for instance, beforehand, and people had it without the square root and stuff like that. And then you see that there are boundary layer widths that you can calculate and so on. And the trick is really to map it to a model where you have only two directions, left and right. In reality, the particle is diffusing rotationally, and you can write down all the equations. But the way how you approximately solve these equations has to be guided by the simple model. If you do it like this, you get a physically sane approximation, and then you get all the results. Like it looks like, if you compare it to simulation, it looks like almost exact. There are super tiny deviations only, and it works quite well with the experiment also. So that was an interesting story, and I realized that I'm running out of time for the third topic with a delay. So I just give you the ideas of that. So if Frank and his group, if they steer these particles, they have to look where the particle is going or where it's heading, and then they apply the laser or not. And this the machine that does it, that evaluates the feedback loop, needs some time. So typically there is a small time delay, and they have played around with this to find out how important it is, and they can artificially increase it. And then they get a lot of interesting things that are due to the delayed interaction. So if I have a delayed reaction to some other particles, say, or some environmental conditions, that's another breaking of a symmetry. Because again, it's then non-reciprocal, and you could imagine that this makes a lot of stuff more complicated, and it does in general. And there is I just give you here the overview. So the paper is this Olubach paper here in New Journal of Physics, is about, again, a trick to basically look at a limiting case of this delayed differential equation problems, where you can map it back to equilibrium, in some cases using, again, other effective temperatures. And there is another PRL where they discuss like conservative systems, which is also, like, it seems to be a hot topic in that field also, where they look at systems without damping. So to some extent, we can basically then say we play the old trick again and understand a bit where we are. But in general, we are in a situation where symmetries are broken so strongly that we can't map it back to any equilibrium, and we can't play such tricks. And then we go to the swarms, and the last example would be the vortex motion. So let me just very quickly show you. I skipped this. This is about swarms. Andrea Cavagna has worked a lot on that, and he's shown that the Witschek model doesn't properly describe the swarming transition to the collective behavior. And we have recently also, in this paper here on the left, this PRL, we have shown that apart from inertia of the swimmers or flies or midges or whatever, there can also be delay, and it leads to very similar effects for the critical behavior, as he has found. And then the last example that I wanted to mention is, like, if we go back basically to this nudging here, and you look at a particle in the center, which is an obstacle, and the active particle wants to go to the center, but because of the delay, when you measure it, you say, okay, go to the center. But when the motion is really applied, then the particle has moved a bit and is not going exactly to the center, but slightly off center. There's an angle theta here. And if you do this, then you get this, if there is super small delay, if you are very fast with your routine, it does what it should. But if you have a large delay in the problem, the particle starts to do something else. In fact, you get a bifurcation, and the particle goes left or right turns, and you get some chiral symmetry breaking, so to speak, here. And you can do this with many particles, as you see in this final video. That's really the last thing I want to show you. And you see that these particles are constantly turning. And if you search the web for puppies and pinwheels, you will find that little dogs, if you give them food, they do the same thing. And it's quite funny to watch. So you get a bifurcation of left turning and right turning motions here. And there's something maybe interesting also in with respect to flow problems that you have in mind. And that's why I wanted to show you this last video. And you can, like, that's what Frank is doing. These are all experiments you're seeing there. When you have more particles, it gets even more interesting, and they are moving in different senses, as you see. And hydrodynamics is probably, like, solvent hydrodynamics is playing quite probably an important role in this effect. And with this, I want to stop, and sorry for running so long, and thank you for your attention. And here's just a summary, but I don't read the summary because I'm already over time, and I rather want to take some questions from your side. Thank you very much.
Thank you, Klaus. Don't worry for the time. There have been some questions during your talk, so it's fine. And so maybe Massimo, do you have a question? I see your.
Oh, I was clapping my hand, sorry.
Okay.
Take out there. Yeah.
Anyway, we have 5 minutes for other question. So maybe also if you want to type in the chat.
Yeah, if it's not an urgent question, I could just go through the summary quickly, and maybe then a question comes up.
Yeah, okay, fine, thank you.
Maybe do this. So, okay, I showed you how the microswimmers in the real world work. If especially these hot microswimmers. And I showed you that much of what they are doing engine-wise can be subsumed into effective coefficients, even though there are some subtle symmetry breakings going on, but they don't spoil that most of the time. And that allows us to also define something like active heat. So a mapping, as Massimo pointed out, rightly pointed out, of the non-equilibrium diffusion of these particles to a effective temperature again. So it's a higher level effective temperature now, which rescues the second law from being violated, as some people have thought in the literature. And then, of course, we can have not only homogeneous activity or switching the activity in time, but we can switch the activity in space. And that was the question of the activity landscapes or gradients, and what kind of density polarization patterns come up at such a boundary between active passive. And maybe one thing for you to take home is that there is, of course, at the boundary, there is this accumulation of polarization, which amounts to swim pressure. And an interesting aspect that some people haven't easily digested is that there is the swim pressure, but as soon as the particle comes to the other side, it's gone. So there is swim pressure around this boundary, but it's not exerted onto the other side. There is no pressure exerted from the region where it is to the other side. That's quite unconventional, and people often don't get this right. And they think they can make force balances, thermodynamic force balances or something like that, but that's not the case. These polarization patterns are entirely driven by non-equilibrium fluxes, and they can't be used to really set up a static force balance or something like that. And the last point was then delay, which drives the system again far from equilibrium, breaks symmetries like reciprocity and so on, and can lead to all kind of difficult motions. But yeah, we have just started to explore some of those difficult motions, as you saw in the movies. Yeah. So now I tried to summarize. Maybe that raised more questions. I don't know. There is one in the chat, maybe.
Yeah, there is a question in the chat.
Yeah, okay, the applications. Well, I'm not so sure, whether, especially given the discussion today in the parliament in Germany, whether I'm really fond of drug delivery in my body. But yeah, in principle, you could think using it, but you could, for such practical applications, any way of moving a particle would be right. I think the thing that we are exploiting a lot, especially in this experiment with the active-passive boundary, is that we can get the particles there without applying forces, because there could easily be artifacts, of course, if you confine the particles by forces, and then you wouldn't know, I mean, is this now only because there is an active passive boundary, or because there is a force also acting on the particle? And so we can be sure in the experiment to have a completely force-free situation. And that's the important thing to us. So I think like this nudging is a really handy method for many things. But for me, the beauty of it, or the greatest power, comes in if you, on this conceptual level, where I say I can create certain patterns without forces. So then I understand the physics of the pattern, and I know for sure there is no force. I know there is swimming, but there is no force. And that was really what was important for us.
Okay.
Can I do a quick, just a question?
Okay, yeah, sure, Massimo.
Actually, I was very curious from your very first slide, the one on the sand and so on. Can you show it again?
Yes. Let me see.
Just because I do a screenshot for the names for finding the papers. Okay, and if you have, I mean, just in 1 minute, can you tell us a bit what people from, turbulence could bring to this?
Yeah, the difficulty is the boundary layer physics. So it's a turbulent boundary layer, but there is, depending on the grain size, there is a viscous sublayer on top of the ground, and this the importance of that depends on the wind strength. It depends also on the grain size, as I said, because it affects the roughness of the flow. Then if you get transport, you change the roughness length, basically, meaning that also there is a feedback on the boundary layer. And so in the beginning, when I entered this field many years ago, and we explained why the desert is not flat and why you get a symmetry breaking that makes the dunes, it was related to spontaneous symmetry breaking in the flow field. And that was kind of all simple and easy, and people have in the meantime all bought that story, and everybody knows that, basically. But the problem is really how you get from the symmetry breaking of the wind also to, there is another effect, which is the wind picks up sand, and it can pick up more and more the stronger the wind is. So over the terrain, if the wind goes over the terrain, the wind is changing, so it can pick up more grains and saturate itself. The flow can saturate itself more and more. But there is a transient with saturation, because it takes some time and it takes some distance for this to come up. And this is called the saturation length then. How long does it take for more sand to be picked up when the wind is stronger, or sand to be deposited again when the wind gets weaker? And for this length, you have to do a microscopic calculation if you want to really understand the phenomenon on the symmetry breaking that goes on or goes off, or is there or is not there. And this is what is not fully understood. There is some overall understanding of this basic idea, but like what, for the small ripples, for the beach ripples, and for the smaller structures, there is no agreement. There is a lot of debate on Mars. What mechanism is the symmetry breaking mechanism for these ripples to show up? Is it in the fluid? Is it in the fluid flow? Or is it something with the hopping of the grains on an uneven ground? So there's not the symmetry breaking mechanism. There's no agreement whether it's hydrodynamic or not. That's the state of the debate. It's not clear on Mars, and my opinion is it's not. People haven't understood it on Earth. They thought they had understood it, but it's not.
Thanks a lot.
I hope this helps to clarify a bit.
Yeah. I mean, just to have a better idea. Thank you.
We still have a question from Bernard.
That's very nice. Yeah. If I
Thank you,
get the
Bernard.
time, I would like to take it if possible.
Okay, so Bernard, please, a quick question, if you can. We cannot hear you, Bernard.
Maybe now?
Yeah.
Sorry. I just wanted to say related questions occur in Chladni figures. The grain, so it's still not understood why the grains settle on the nodal lines. Grain collisions, the granular dynamics of the systems, small grains, determine whether the nodal line is a stable or unstable fixed point. And it's not known.
Mm-hmm. It's not known in detail. The principle is if you have just two places with different amounts of grains, they tend to jump higher on a hard ground than on a soft ground. So if you have two boxes and you shake them, and there is a lot of sand in one box, the shaking there is more dissipation. Because the restitution coefficient is low in the sand. If a sand grain drops in the sand, it loses most of its energy most of the time. So that's why if you have two boxes filled with equal amounts of particles, they tend to go all into one box. Because if there is more to start with, it's more dissipative, and so they will all come over to this side. And this is the main principle. But as you say, the details of this are not super well understood. And that's, of course, also an aspect in our discussion, that the hopping of the grains, whether they rebound from the surface or whether they get trapped, and how much the sand bed is agitated by this whole process and how important this is, it's not under control. There are a lot of ideas and theories, but it's not under full control.
But the Chladni figures are a bit simpler because
no wind.
The collisions with the plate are not so important, so it's just the collision.
Yeah.
Thank you.
Okay, so thanks again, Klaus, for your interesting talk.